Cool. Thanks for being here, everybody. My name is Ken Thompson from the University of Toronto in Canada, and today I'm going to talk a little bit about how the evolution of defense can change selection on flowers. And so flowers are the sex organs of plants and represent one of the most remarkable examples of adaptive structural diversity that you can find in nature. And a lot of that diversity can be attributed to the plant-pollinator relationship, where a lot of flowers are adapted to facilitate pollination by a particular agent or a pollinator. So in this example, the penstemon has sort of specialized flowers to attract and facilitate pollination by hummingbirds. And so this results in a lot of floral traits, like in this example, flower size, being explicitly linked to pollinator attraction. So you might have a plant with large flowers that attracts more pollinators, and a plant with smaller flowers that attracts relatively fewer pollinators. And because this relationship is mutualistic, there will be selection to increase the frequency of this interaction. So if a plant has small flowers, and there's only pollinators around, given time and selection, a plant may evolve larger flowers to attract more pollinators. But there are many floral adaptations that can't easily be explained as adaptations to facilitate pollination, like these thorns in the yellow star thistle, which are better explained as adaptations to reduce herbivory. And as with pollinators, a lot of floral traits are actually linked to herbivore attractiveness. So a plant with large flowers might actually, in addition to attracting more pollinators, might attract more herbivores. And on the same scale, a plant with small flowers might attract fewer herbivores. And because this is an antagonistic relationship, there should be selection to decrease the frequency with which this interaction occurs. So if there's only herbivores around, given time and selection, you might expect a plant with sort of moderately sized flowers to evolve smaller flowers to decrease attractiveness to herbivores. And so for a lot of floral traits, it's really the balance between selection imposed by pollinators and selection imposed by herbivores that is responsible for most selection on flowers. So in this hypothetical example, if we have an equal amount of pollinated and herbivores, you can imagine that their selective pressures might cancel out and you might not actually get any evolution of the flowers. So for my talk today, I want to focus just on one question. Can expressing anti-herbivore defenses change selection on floral traits? And I think that it should, and here's one way that it can happen. So if we take the same plant with its herbivore and pollinator community intact, following the expression of a reasonably effective defense, you might expect that its herbivore community to be knocked down. Now that there's no more herbivores around, pollinators become a relatively more important agent of selection on flowers, and given time and selection, plants may freely be able to evolve large flowers. And that's just one way that that could happen. This is purely hypothetical. So, what did I do? I chose to study Trifolium repens, or white clover, which is a very common perennial invasive weed that has very dense inflorescences right here with small flowers. These are sort of close-ups, but most often it is seen looking sort of like that. And the reason I chose to study white clover is because it possesses a genetic polymorphism for cyanogenesis. And cyanogenesis is the release of hydrogen cyanide following tissue damage, which is a compound that disrupts the electron transport chain. And it's present in both leaves and flowers. And what I mean by polymorphism is that some plants don't have cyanide and some plants do. It's really that simple. This is a polymorphism that's regulated by two loci, each with two alleles that are dominant in the presence or absence of a gene. And it's extremely easy to screen for these genes by just putting tissue in wells, putting some special paper on top, and putting it in an oven for a little bit. And it's really, then you tell what the genotype is. So I conducted a pretty traditional ecological genetics experiment at the University of Toronto's Koffler Scientific Reserve, where I grew plants from 185 genetic families with up to 5 clones of each of those families, present in the array for a total of 906 plants. Of those 185 families, 64 had cyanide, so are defended or cyanogenic, and 121 did not have cyanide and so were undefended. And these frequencies represent sort of what we find around in clover populations around this field site. I measured herbivory, 7 floral traits, and 2 components of fitness on all these plants. So I made visual estimates of herbivory twice during the growing season on sort of 5 haphazardly chosen old leaves. So in this extreme example, there's 0 damage here and 50% damage here, and there were obviously bigger variations between there. I measured 7 floral traits, but I'm going to focus on 3 today. So the width of banner petals, so the width of these single flowers here, and the length of banner petals, and also on the number of flowers within flower heads or inflorescences. I also measured this length and width, or the height and width of flower heads, the date of first flower, and the total number of flower heads that a plant produced. I made measurements of two components of fitness. So I measured female fitness, which was seed mass, very correlated with seed number. And I measured male fitness, which I did as the number of pollen grains per flower. So this is sort of pre-selection. And I'm going to focus today on female fitness, which is where all the interesting stuff was happening. And so my selection analyses are going to sort of look like this, and they're just genotypics, multivariate selection gradients, following the traditional Landy and Arnold framework, but instead of mean individual values, I'm using mean family values. So these graphs are on the y-axis is relative fitness of a genotype, and on the right is standardized trait values. So, for example, maybe small values on the left and large flowers on the right. And so, in this example, families, so a single dot, with higher trait values, bigger flowers, have higher fitness. So we say that there's direct selection for larger trait values in this hypothetical example. So there's a positive beta coefficient, which tells you something about the strength and direction of natural selection. And specifically, the way I'm going to show these is by breaking them out between undefended and defended plants. So on the, I guess that's the, I don't know, left or something. On the left, you have undefended plants, and on the right, I'll have defended plants. And then I'll have this term, which is very important, the interaction p-value. So in this example, both of these two morphs are experiencing positive natural selection, and so because selection is acting the same on these two morphs, the interaction p-value might be non-significant. However, if they experience different selection, then you expect to see a significant interaction p-value telling that natural selection is behaving differently or acting differently on plants with and without defense. Okay, so before I get into the selection results, it's just important to say that in the field, cyanogenesis actually did reduce herbivory. So in surveys both during the early and late growing season, we found that defended plants had less damage on their leaves than undefended plants. And the effect size here is about 19% lower damage in plants with defense. Okay, so on to the selection. So when we looked at selection on the length of banner petals in undefended plants, we saw pretty strong selection for longer banner petals in undefended plants. But when we looked at plants with defense, we found that there was no selection on banner petal length, and the interaction p-value is significant here. And so I'm just going to speculate about what I think is going on. So in the field, the typical pattern of herbivory on flowers is to just cut off the top of the banner petal. So you can see here this banner petal would have been a little bit longer, but herbivores knocked it down. And so I think there might be selection to tolerate herbivory happening in undefended plants, and I'll explain what I mean. So if you have a plant with a relatively short banner petal, following herbivory, it might have a banner petal that is too short to actually attract pollinators, and so the plant might not be doing pollination. But if you had a plant with a longer banner petal to start out with, following a similar amount of herbivory, it might have a banner petal that's still long enough to sufficiently attract pollinators. And you wouldn't have very much herbivory on banner petals in defended plants, so that might be why selection is not happening. So banner petal width, we found trending towards negative but non-significant selection for narrower banner petals in undefended plants, and trending in the opposite direction but still non-significant selection for longer banner petals in defended plants. The interaction p-value is significant, so when we look at these two individually, although we can't detect selection, we can still say with some confidence that selection is acting differently here. I'm not going to interpret what's going on though, because we're not able to detect selection on either of them. Okay, so lastly, selection on the number of flowers within flower heads or inflorescences. We found weak but positive and significant selection for more flowers within inflorescences in undefended plants. And remarkably, when we looked at defended plants, we found that selection for flowers within inflorescences was almost 3 times as strong. And this is also significant again. And so I'm going to speculate again about what I think is going on. So I think there might be diminishing returns on increasing flower production in undefended plants. And so if a plant starts off with a small amount of flowers in the inflorescence, it will have a relatively small amount of seeds that it can produce, maybe 6, and it might lose some of those to herbivores, so maybe 1. If a plant produces more flowers, it will have more ovules and more seeds, but it might lose more of those to herbivores. And so if the increased attractiveness to herbivores, okay, because of larger flowers outweighs the fitness gains of having more flowers than inflorescences, you might see these diminishing returns. So to sum that up, there's a benefit to having more flowers, but maybe increasing cost of attractiveness to herbivores. And then you might not see this cost in defended plants. So if you have a plant with inflorescence with few flowers, you'll have few seeds. If you have an inflorescence with more flowers, you'll have more seeds. So there's the benefit of having more flowers without the cost of increased attractiveness and loss of seeds of herbivores. Okay, so to sum up, we found that herbivore defenses can significantly alter selection on flowers, and more important, or maybe more broadly, variation at these single major effect loci involved in defense can really change the way that selection's acting on flowers, because these two groups really only differ at one or two loci. And but there's still a lot of speculation happening, and we don't exactly know what's going on. So we're continuing this work, and I'm working with this guy James Santangelo, conducting a similar experiment to what we did last year in the field, where we're doing a genotypic selection experiment, but simultaneously manipulating pollination and herbivory. So that's all. I just want to say thanks to my great lab mates and supervisor, funding, and I'll be happy to take questions if we have a few minutes.
Did you look at the relationship between any floral traits and herbivory?
Yeah, so there, I didn't talk about that today, but there were some significant correlations between floral traits and herbivory. So plants with, I think, larger flowers did have more herbivory on them. I don't think I have those in my secret slides, but yeah, those are going to be, we have those in the paper.
I was just wondering about seed set for plants that were not only either defended or undefended, and also not exposed to herbivores at all, so had no kind of or pollinators. Pollinators, not herbivores.
So is the question, how does seed set differ when plants aren't exposed to herbivores? So in my field experiment, there were actually no differences in fitness between the two. But in previous experiments in greenhouses, there's been shown that in the absence of herbivores, plants without defense have higher maternal fitness and produce more seeds. So there seems to be a cost of producing these defenses in the absence of herbivores that affects your maternal fitness. Okay, thank you.